Hello everyone, my name is David Medina and today I'm going to talk about accelerometers. Have you ever wondered how do we know that there is an earthquake happening? How does your phone notify you? Or how can we know where the earthquake started? Have you ever wondered why the screen of your phone turns on when you pick it up? Or how does it know that the screen must change orientation when you rotate the screen? All of this is thanks to a small sensor called accelerometer, which sends a signal to the device when the position has changed, or when it detects vibration. It can also help a vehicle deploy its airbag when it senses collision. Now, what does it measure? An accelerometer is a tool that measures proper acceleration, which is the rate of change of velocity of a body in its own instantaneous rest frame. For example, an accelerometer that rests on the surface of the Earth will measure an acceleration due to Earth's gravity. By contrast, accelerometers in free fall will measure zero. Single and multi-axis accelerometers can detect both the magnitude and the direction of the proper acceleration as a vector quantity, and can be used to sense orientation because the direction of weight changes, coordinate acceleration, vibration, shock, and falling in a resistive medium. Accelerometer technology begins with the postulation of Newton's law describing the acceleration principle, and in the 20th century there has been various breakthroughs that allowed the development of the accelerometer as we know it. It starts as a resistance strain gauge, being used like dynamometers for measuring acceleration mainly in shock and vibration. Then the piezoelectric transducer took place, and in 1953 was given the status of accelerometer. Nowadays, with MEMS technology, accelerometers can be integrated in small devices like our phones or tablets. In this development, we can find great names like MIT, Texas Instruments, and Brühl and Kea. Now, let's explore the principle of functioning of accelerometers. The most basic mechanical accelerometer is a damped mass on a spring. When the accelerometer experiences an acceleration, Newton's third law causes the spring's compression to adjust, and exerts an equivalent force to the mass to counteract the acceleration. Since the spring's force scales linearly with the amount of compression, according to Hooke's law, and because the spring constant and mass are known constants, a measurement of the spring's compression is also a measurement of acceleration. Resistive accelerometers use a strain gauge measuring in change of resistance and converting it to an electric signal with a Whitson bridge. These sensors are used in application when high precision is needed. Capacitive accelerometers on the inside have a moving mass and a static mass. When acceleration is applied, the moving mass moves away from the static mass that is electrically charged. The separation makes the capacitance vary, then generating an electrical signal proportional to the acceleration. These sensors are commonly used in portable devices due to their low energy consumption. This type of accelerometers contain a piezo crystal such as quartz or PCT that generate an electrical current when under strain. The deformation of the crystal due to acceleration provokes a voltage which is proportional to the applied acceleration. This type of sensors are well known and used for being highly sensitive under fast response, ideal for application with high frequencies like vibration testing. Similar to the piezoelectrical sensors, a piezoresistive accelerometer has a material that changes its internal resistance when deformed. This change can be converted to voltage using a Wheatstone bridge. Microelectromechanical system accelerometers are miniaturized devices that use either capacitive or piezoelectrical technology to measure acceleration. They have a small mass suspended in between flexible structures which move in response to the acceleration. These sensors are used in every phone and consumer electronic devices due to their low energy consumption and very low manufacturing cost in big scales. There are also other types of accelerometers such as Hall effect or Thelma accelerometers. Accelerometers with analog interface show accelerations through varying voltage levels. These values generally fluctuate between ground and the supply voltage level. An ADC on a microcontroller can then be used to read this value. These are generally less expensive than digital accelerometers, although in industrial application is accustomed to use a signal of current instead of voltage because the signal won't change in big distances. Accelerometers with a digital interface can either communicate over SPI, which means serial peripheral interface, or I2C, integrated circuits communication protocols. These tend to have more functionality and be less susceptible to noise than analog accelerometers. A diverse array of accelerometers are available, each meticulously designed to meet specific requirements. Manufacturers such as Kiesler, Texas Instruments, Honeywell, and Bosch offer a wide range of models, encompassing measurement acceleration from 1G to an impressive 1000G. These sensors come with varying specifications and features, making them adaptable to a multitude of applications. The pricing of these sensors also varies depending on the selected model and its unique attributes. Let's talk about real-world applications. We can find accelerometers in many different applications, such as drones for controlling movement and speed, wind turbines, assembly lines, and every type of robot, all kinds of vehicles, smartwatch for running and monitoring health, smartphones for snooze or rotating, VR headsets, video game controllers, treadmills and other gym equipment, vibration and shock testing for machinery, seismic activity, satellites, and many other applications. Thanks for watching.